This summer, I had the pleasure of working in Dr. Kimberly Hall's quantum optics lab, where she focuses on quantum dots. These are man-made nanoscale bubbles that are formed when indium arsenide is deposited onto gallium arsenide. Quantum dots confine electrons in all three spatial dimensions, which leads to discrete atom-like energy levels. In our experiments, we use an ultrafast laser to excite an electron in the quantum dot to a higher energy state. When the electron drops back down to ground, a photon is emitted, which makes quantum dots a robust source of single photons. This is something essential for quantum cryptography and optical quantum computing. The excited and ground states of the electron form a qubit, which is a quantum equivalent of the classical 0-1 bit, but instead of just 0 and 1, a qubit can have a state of anywhere in between these two values. One great way to visualize this is using the block sphere representation, which you can see on the right-hand side. This is a unit sphere, with the south pole being the ground state and the north pole being the excited state. By changing the characteristics of the laser pulse, we are able to choose an excited state by driving the system to an arbitrary superposition of the states 0 and 1. To get the cleanest quantum control, our system is pumped resonantly, which means that the laser and quantum dot have the same frequency. However, this creates a problem because in doing so, the emitted photon has the same wavelength as the pulse, which makes it difficult to detect. In order to measure the photon without interference, we wanted to make a single photon source using a pulse that had a hole at the center of the spectrum, called a bichromatic pulse. In our experiments, pulse shaping is done using the SLM, which stands for Spatial Light Modulator. This is found in the diagram here. The action of the SLM can be described numerically by amplitude and phase mask functions in the Fourier domain. So, we defined a bichromatic amplitude mask, which was two Gaussians multiplied together. As shown in the figure on the left, this created a pulse with a hole at the center, which is exactly what we wanted. We then ran our code using this bichromatic mask for a 2 MeV hole. As you can see in the figure on the right, we were able to get inversion at a pulse area of about 1.3 pi, thereby creating a high brightness, on-demand, single photon source using a bichromatic pulse. Mission accomplished. Thank you.